Hey everybody, Dr. A here, and in this video we're going to be providing some background information and exploring a few simple examples of how to sketch qualitative influence lines for beams. Now, what do we mean by qualitative? Well, anytime you hear the word qualitative, that's kind of a little bit in opposition of quantitative, okay? So when we think of a qualitative influence line, we're thinking of just the shape of the influence line without any real numerical analysis or numerical values on the plot itself. So when we sketch the shape, the general shape of an influence line, if you ever hear the word qualitative, that kind of refers to that, just basically the shape of the influence line without having to show a whole lot of equilibrium calculations. Now, qualitative influence line sketching was developed by Heinrich Muller-Breslau in 1886, and it's named after him now. Specifically, it's named the Muller-Breslau Principle. So how do we do this? What's this principle say? Well, it turns out that the influence line for a particular effect, so that could be reaction, shear force, or bending moment, is the same scale. So when you plot it, when you sketch it, it's going to be the same scale and the same shape as the rigid body deformed shape of that beam when acted upon by the effect. Okay, so maybe pause the video, write that down, and absorb that sentence because it does sound a little confusing at first, no doubt. Okay, so what do we mean by that? Well, what we do is we remove the beam's ability to support that applied effect. So we remove the beam's ability to support a reaction, if that's the effect we're interested in. If we're interested in a shear force, we remove the beam's ability to support internal shear at the desired point, so on, okay? And then what we do is we place the effect on the beam like it's an applied load. And then we let that beam rigidly deform, okay? And the rigid body deformed shape will be the shape of the influence line. Now, you notice I've said this kind of strangely. I've said rigid body deformed shape a couple of times. What do we mean by rigid body deformed? Well, that means that we are assuming, for the purposes of the Muller-Breslau principle, that the beam is not curving, it's not flexing, it's just rotating or translating or displacing. So we're assuming that there will be no curvature of the beam when we deform it, okay? And we'll see that in an example in just a second. So let's turn the page and let's explore some of these simple illustrative examples. So qualitative influence lines examples. Sketch the shape of the influence line for each beam for the load effect. So I'm giving us 3 different beams here and some load effects that we want to sketch the influence lines for. So beam A is a simply supported beam, and we want to sketch the qualitative influence line using the Muller-Breslau principle for BY. Beam B is a simple beam with a little cantilever overhang, and we want to sketch the influence line shape for AY. And then beam C is a simple beam with a double cantilever overhang, and we want to sketch the influence line for VB and MB. So that's the shear force and then separately the bending moment at point B. So let's do this one at a time. We'll start with beam A, okay? So I'm going to turn the page, and I'm going to say solution. I'm going to say beam A. So I'm going to go ahead and redraw that. Okay, and I believe we had a roller at point A and a pin at point B, right? And so what we're looking for is the shape of the influence line for BY. So what we're going to do here is we're going to say remove the beam's ability to support BY, then place BY on the beam like an applied load. Okay, so if I remove, this is point B here, if I remove point B's ability to support a By reaction force, what am I doing? Well, if I resketch this beam and I just leave A alone, okay, I'm leaving A alone over here as a roller. If I say, hey, all of a sudden point B is not able to support By, what have I effectively done? Well, what I've effectively done is I've turned that pin at B into like a slotted roller connection. Okay, I've turned it into a slotted roller because now if I reimagine this as a slotted roller, I can still develop a BX, right? We're not talking about BX. BX, we don't want to mess with BX. But now, guess what? By will not develop here because this roller can roll upwards or downwards, okay? So I've removed point B's ability to support By, and to do that, I swapped out this pin for a vertical roller, okay? So BX could still develop, but By cannot. Then, what do I do then? Place By on the beam like an applied load. So watch what I'm going to do. I'm going to place By here like an applied load, and I'm going to let this thing deform. So how is this going to deform as a, quote, rigid body? Well, this point B, is going to roll upwards, okay, because now it's unrestrained in the y direction, and it's going to pivot about this point A. And this beam segment is going to remain linear. It's not going to flex or bend. So watch what's going to happen here. The shape of the influence line will look something like this, and this is going to move upwards here, okay? And this shape, this linear segment, is the shape of the influence line for By on this beam. And that's it. It's that simple, okay? We just remember this handy little sentence here. All right, let's do the beam in part B together, okay? What did this look like? This was a simple beam with a cantilever overhang, and we were interested in the qualitative influence line for AY. So I'm going to resketch this for my reference here. Okay, let me sketch that a little bit better for us. Okay, and we have a roller here at A, and I think we had a pin back here at B, didn't we? Yep. And so this is point B, this is point A. And so what am I going to do here? Well, again, I ask a similar type of question that I did before. I'm going to, or I make a similar statement as I did before. I'm going to remove the beam's ability to support AY, then place AY on the beam like an applied load, okay? Let me move this sentence up just a little bit just to give me a little bit more room later on. Okay, so how am I going to do this? Well, this point A is already a roller, so it only could support AY. So if I remove point A's ability to support AY, what am I doing? I'm just completely deleting the roller. I'm going to just remove it altogether. So if I think of that as removing it altogether, then I'm going to have this beam here with just this pin back here at B, and then I'm going to place AY at point A, and then I'm going to watch this thing deform as a rigid body, which means, again, this segment is going to stay straight. It's not going to curve or bend. It's just going to rotate about a pivot point. What pivot point is it going to rotate about? Well, that pivot point at point B right there. Let me draw that a straight line a little bit better for us. Ooh, that did not turn out right looking. There we go. And again, this thing displaces up right here. So this is the shape of the influence line for AY for this particular beam, okay? Now, what about the beam C, okay? We had this double cantilever overhang, and we were asked for two things, right? So I'm just going to kind of get more straight to the point here. We were looking for the shear force and the bending moment at point B. Let's look at the shear force first. So what are we going to do? We're going to make a similar statement. We're going to remove point B's ability to sustain a shear force. So if I do that, if I remove point B's ability to sustain a shear force, what is that going to look like? Well, I'm going to keep my support reactions there, but what I'm going to do is I'm going to cut point B just a little bit, and I'm going to put a roller guide at point B, okay? So think about that. If I want to remove point B's ability to support a shear force, I make a cut here and I put some rollers here to allow for shear force not to be supported, okay? Think about, support reactions that we've studied in statics and mech of materials. Then what I do is I enact a shear force VB and VB on either side of this cut. Why do I put this on twice? Well, remember, for shear and for moment, for that matter, there's a discontinuity that shows up at the points of interest. And so I'm going to put this VB with equal magnitude but opposite directions on each side of this roller guide that I've inserted here, okay? And I'm going to follow the sign convention that we follow for internal loading. So VB on the left points down, VB on the right points up. So that causes this segment to rotate what? Rotate in a clockwise fashion. So what's going to happen here, I'm going to get this kind of pivoting here, and I'm also going to get pivoting here, okay? And then I've got this discontinuity that shows up right there at the cut. And so look at that. This right here is a piecewise segment, two parallel segments generating that influence line for shear. And again, we've seen that before in a previous video example where we saw influence line for shear creates two parallel lines. Okay, now that's shear. What about moment? Well, we also had a moment problem for the same beam. So I'm going to come over here. I'm going to kind of redraw this beam for us again. So now, how do I sketch the qualitative influence line for the moment at point B? Well, again, ask yourself, or make that statement again, remove point B's ability to support a moment at that spot. So what do we do to point B to prevent it from supporting an internal moment? Well, what causes a prevention of internal moment support? That would be a hinge, an internal hinge. And then we are going to place MB on the member at that internal hinge, okay? And like an applied load. And we're going to do same magnitude, opposite direction on each side of that hinge. Again, we're capturing a discontinuity in the moment. We explored that in the previous video. And so when we do that, what happens here? Well, again, you get this kind of this rotation or this pivot point about each of the two supports here. and this is your qualitative influence line for the moment at point B. Okay, so these are fun little problems to do, and if you follow these basic rules, remember, remove the beam's ability to support the blank, the effect, and then place that effect on the beam like an applied load. Then that's all you got to do. You just got to remember those two sentences that are kind of wound up as the Muller-Breslau principle here. So that concludes this video. Hopefully you found it helpful. If you did, please hit like and subscribe and be on the lookout for other content like this.